Hello, this is Mr. Gilmore with the 7.6 Part 1 Application Proofs. We are coming to the end of Chapter 7 now with these last two parts. As you can see that we will have a 7.6 Part 2 in our next lesson. But what we're going to see today is some application proofs, meaning we have several theorems that we've encountered this chapter, such as angle-angle similarity, things like triangle proportionality theorem, and we can use these then in some applications to reach some other conclusions within our geometrical properties. So my advice for today is we have three phenomenal theorems that help us to take a shortcut to similarity. Now, I hope you notice that similarity is just as a powerful tool as congruence. It brings more information to us if we can prove two triangles to be similar to each other. And there are three theorems that help us into a shortcut to similarity. And those three theorems, remember, are angle-angle similarity, side-angle-side similarity, and side-side-side similarity. So again, my advice today is use these. Be on the lookout for these shortcuts. That way you can tap into the use of similarity to arrive to other conclusions. Okay, so we begin our application proof section today here with our first theorem on showing that there's actually similarity in trapezoids. So here's what's interesting. In a trapezoid, the diagonals cut each other proportionally. Let's take a look at the diagram below. In our diagram, we do have a trapezoid ABCD, and already given to us are the drawn-in diagonals BD, AC, and such that they intersect at point M. Now, so our given is just standard. Here's triangle or trapezoid ABCD. We're going to prove that those two diagonals, notice that how they cut each other. They cut each other into four smaller segments, BM, CM, DM, and AM. What we're going to prove is that those four parts are proportional, meaning, respectively, as we find here in our proof statement, BM ratio to DM is going to equal to CM ratio to AM. And we're going to prove that using what we've learned this chapter, and that is similarity. So let's take a look at the proof here together. So again, we have our trapezoid ABCD, such that our two diagonals are drawn in BD, AC, and they intersect at point M. Now, where we start, obviously, is just with our given. We have trapezoid ABCD. Now, from our given, we know that by definition of trapezoid, that BC and AD are parallel. And because they're parallel, notice that then we are cutting those parallel lines with several transversals. And when we do that, we form angle relationships. And one of the angle relationships we're going to tap into is the alternate interior angles that are formed. Because the lines are parallel, we then find we have pairs of equal alternate interior angles. So I'm going to point these angles out to you. So the first pair that I see is angle MAD and angle MCB. Those two angles there are alternate interior, and we know them to be equal because of the AIAC, the alternate interior angles consequence. Do that again with the second pair of angles here. We have MDA and MBC. Those two angles are equal to each other. And those are also alternate interior angles that are equal by AIAC. And what does that mean? That means we do have two angles of one triangle equal to two angles of another. And that is similarity. We have angle-angle similarity we could tap right into. So in step 3, I have triangle ADM is similar to triangle CBM. And with our similarity, we can tap into the definition of similarity and grab, we have proportional sides. Specifically, I'm grabbing what the ratios are between these two triangles. So I have BM ratio to DM, CM ratio to AM. Those are corresponding sides, which means they are, in fact, proportional. And there we have it, the end of our proof for the similarity in trapezoids. Now, we're going to move on to our next proof, but before we get to that, I need to introduce to you a new segment that can be formed in the interior of a triangle. This segment is called an altitude, okay? A triangle altitude is a segment from a vertex to the line through the opposite side perpendicular to that line. I know it's kind of a lengthy definition, but it's a very simple definition in sense of illustrating this. In our triangle below, ABC, what you're doing is you're creating a segment from one vertex to the opposite side such that it is perpendicular to that opposite side, or in some cases, it will be perpendicular to the line containing the opposite side. And that's really what's summed up in the definition there. So down below in our diagram, BX is what we call an altitude. Notice that BX is formed in our triangle ABC such that from the vertex B, that segment BX is perpendicular to the opposite side of our vertex vertex B. Now, we're going to prove something interesting about the altitudes of triangles. So as it turns out, here's our next theorem. The altitudes in similar triangles are also proportional to the sides of the two triangles. So if two triangles are given to us as similar, then their respective altitudes are proportional to their sides. So in our diagrams below, there's a lot going on there. I'll unpack that for us here. In our diagrams below, we have triangles ABC and RST, such that we have the altitude BX in ABC and the altitude SY in RST. And what we're already given about these two triangles, look at our given, the conditional. If two triangles are similar, meaning we already know that the two triangles ABC and RST are similar. What we need to prove then is that the ratio of our altitudes, BX to SY, is the same ratio as the sides of our triangle AB and RS. Now, a lot of students make a mistake here thinking, oh, since the triangles are already similar, that means everything is proportional. Well, not quite. We need to actually prove that everything is proportional. We need to prove that BX and SY are in fact proportional to sides. I can claim all three sides are proportional to the triangles, great, but BX and SY are not part of the three sides, which means we need to find a way to show that they are also proportional. So let's take a look at its proof. Okay, so the proof of our proportional altitudes. Again, I left a lot of our given out on the last slide. I went ahead and put it in here for our two-column proof. So in step one, right, we are given that triangle ABC and triangle RST are in fact similar. So you notice that it's in the given. I've stated that. Also, I'm stating that BX and SY are altitudes of each of their respective triangles. I'm also stating that in the given as well. Now, remember, our goal is to show that the altitudes are proportional to the sides. And the one way we're going to do this, let me go ahead and highlight what we're going to do. We're going to find that this triangle here, ABX, that triangle given to there, and this triangle here, RSY, we're going to prove that that pair of triangles are also similar. So we know the entire triangles are similar, but let's show that these two triangles that are formed, ABX and RSY, are also similar. If we can do that, then we can show that the altitudes are in fact proportional to the given sides of our original triangles, ABC and RST. So where we begin is actually grabbing some information from the given triangles, ABC and RST. I can immediately say that, well, I know that angle A and angle R, they're equal. Why? Right from the heart of definition of similarity. That if I already know two triangles are similar, then all their corresponding angles are equal. Okay, so what happens next is from our definition of altitude, we know that BX is going to be perpendicular to AC. And we know that SY, another altitude, is going to be perpendicular to RT. Now, why is that important? Because I'm going to find another pair of equal angles. In step 4, I did save us some tedious work here by combining a few reasons. In step 4, I can immediately claim that this angle, AXB, which we know is going to be a right angle, and this angle here, SYR, is also going to be a right angle. Those two angles are going to be equal to each other. And I combined a few reasons there using the perpendicular lines theorem and the right angle theorem, that we know all right angles are equal, and that if things are perpendicular, then they form four right angles. So what I have in my midst there, using step 2 and step 4, that means I have two angles of one triangle equal to two angles of another. That's similarity. I can grab then in step 5 that triangle ABX is similar to triangle RSY by angle similarity, which means I can tap into the definition of similarity. I know that all corresponding sides are proportional, and then on our case, AB, which is ratio to RS, that is its corresponding side, is in fact equal to BX to SY, its corresponding side. And in fact, if we go back to the big picture, what we really just proved is that the ratio of the altitudes is in fact the same ratio of the sides. In other words, the altitudes are also proportional to the sides of the given triangle. So something interesting happens again when you form these segments on the interior called altitudes, and that is then our proof of proportional altitudes. We're moving on then to our very last theorem, which is actually a theorem of significance. This one actually gets a really cool name. It's called the angle bisector theorem. Let me go ahead and introduce you to it. Here's what this conditional says. It says, in a triangle, an angle bisector splits the opposite side into a pair of segments proportional to the final two sides of the triangle. Now, that's a little bit tricky to unpack. So let's take a look at the diagram and how this unfolds from our conditional. So in a triangle, so we have a triangle down below, ABC. An angle bisector means we already have a segment on our triangle here, BM, that is cutting in through our angle B such that it bisects angle B. So you notice that ABM and CBM are already marked as equal. So an angle bisector, notice that point M cuts the opposite side into two parts, AM and CM. As it turns out, those two parts are in fact they form a ratio, and that ratio is equal to the ratio of the final two sides. Meaning, what are the remaining two sides of our triangle? That would be side AB and BC. Those two sides, we form a ratio. It's the same ratio as the two parts here, and that means we can actually form a true proportion. So let's take a look at how that unpacks in our proof statement. We see that the ratio of CB to AB, that's the ratio of the two sides, is equal to the ratio of CM to AM. Now, how I remember the angle bisector theorem is I like to think of BM as this divider, okay? Notice how it's dividing the entire triangle up into two smaller triangles. I'm going to go from one segment of the divider to the other side of the divider to pick another segment. So if I choose CB first, which is one of my sides of the given triangle, then I'm going to ratio it with the other side of the triangle on the opposite side of my divider. So CB gets ratio to AB. And then for my third side, notice it gets cut into two parts. I ratio it again from whatever side I started on to this corresponding segment on the other side. So CB ratio to AB, right? I'm going from this first side here to the second side over here, right? That's my first ratio. I again have to start on the first side and then go to the second side with my second ratio. So CB to AB is going to be equal to CM to AM. And it's a phenomenal surprise here that happens with angle bisectors within any triangle. That's what's amazing, is it works with any given triangle. Now, I'm not going to walk you through the proof here in the slides. I'm going to leave that up for you guys to do on your own on the worksheet. And the good news is I am guiding you through that. So it's a step-by-step. I help you with these statements, and you give me the reasons on how to prove the angle bisector theorem. So we've come to the end of our lesson 7.6 part 1. You be sure to hop over and find the worksheet to this lesson. Please be working through that. And if you come across any issues and you have any questions, please email me with your questions, and I will get back to you as soon as possible. With that, be good and do good.